Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a recording studio in Vancouver. Quick thanks to our sponsors, National Center of Competence in Research on Dependable Ubiquitous Automation and the International Federation of Automatic Control. Our guest today is Jeff Shamma, professor and head of Department of Industrial and Systems Engineering at the University of Illinois Urbana-Champaign. Welcome to the show, Jeff.
Thank you. Thanks for the opportunity. Looking forward to it.
Well, Jeff, I've been trying to have you on the show for a long time. I'm very glad that we managed to make it happen. There's many ways I can start this episode. I was blown away by the fact that you've done so many disparate things and very original also, but I found very interesting your passions outside of academia. So I'm curious about what kind of connections can you draw between jiu-jitsu and controls and fishing and controls?
Oh, okay. Well, let's start with fishing. I think, there's an element of skill, there's an element of luck, and we tend to attribute more to the skill part than the luck part. And I think that's a clear parallel. There's a lot of luck in an academic trajectory, and yes, there's skill and effort and the like. But I think, and there's also the element of kind of a sudden rush with success. When the fish takes the bait, there's this moment of exhilaration, and I think those kind of moments come in academia as well, of figuring something out, or getting some good news, or seeing one of your advisees or students in class figure something out. Those immediate moments can give you that rush as well. And you always are kind of feeling like it's about to happen, it's about to happen. I know fishing's boring for a lot of people, but for someone who likes it, you can be there for a while thinking that it's about to happen. And that keeps you excited. The jiu-jitsu connections are numerous, and not just to academia, but also to other aspects of life. But I think one of the sayings of my previous school in Atlanta was, don't get tired. And I think that's great advice in general about not getting tired. And maybe I can talk about that more towards the end of the jiu-jitsu connections, because I know I've, in your past podcasts, which I really have enjoyed. My family enjoys it when we take our day trip to Chicago. I don't know if they enjoy it, but they don't complain. And but I know you like to end the show on kind of advice going forward. So perhaps I can make the jiu-jitsu connections at that time.
Sure. So I was curious to understand. So I was reading up lots of stuff online. I've read your People in Control interview, and I was trying to understand, how did you get into controls? So maybe you can share something about that connection.
So here, I don't have one of these ever since I was a child, inspired by blah, blah, blah. And my trajectory of getting into controls was really kind of the path of least dislike. Okay, so I grew up in an academic household, and both of my parents were math professors at our local university in Pensacola, Florida, University of West Florida. So I knew I was going to go into kind of the math sciences. But then, I take the first year physics, and I disliked electromagnetics more than the mechanical parts. So I went to mechanical engineering. Mechanical engineering, wow. Heat transfer, fluids, materials. I met one colleague here in Illinois, and he's the department head of mechanical. He said that he's in thermal fluids. I told him thermal fluids is the reason I went into controls. Dynamics and control was the part that I disliked the least. And then in the master's program, I was in robotics. I was very fortunate to work with a robotics pioneer named Dan Whitney in graduate school, and we did a master's with him. And the part of robotics, well, first of all, robotics in the mid-'80s was a lot less fun than it is now. Just to get one thing to talk to another thing.
Lots of hardware, or?
I was their hardware just to get things to talk to each other. We didn't have motion capture. I had to take measurements using these survey instruments, theodolites.
Okay.
And then after a couple of days of taking measurements, it turned out that the instruments had sunken into the ground, the tile flooring, which had to undo everything. But I got intrigued by the controls part of robotics. And then finally in the PhD, I worked with Mike Athans as my PhD advisor. And that's when I became fascinated with controls. And so it was more of a dislike. And then finally I found, hit my groove with feedback control. And to the point that this is something that I mentioned at talks. I say something obnoxious when giving a talk. I say that feedback control is my domain. And then I invite them to visit feedbackcontrol.com, which is my domain. It's a domain name that I reserved 20 years ago. And up till last month, there was nothing on it other than this domain belongs to Jeff and is hosted by Ayman, who is my brother. But now my son, who works in like mechatronic arts, has taken over the domain. So I can't tell that joke anymore, but because there is actually something on that site now. But from going from not like disliking many things to being really obsessed with controls and feedback control, and to the point that I have to have that domain name for its own sake as a trophy.
So first of all, I'm glad you mentioned it because I did visit that website a few days ago and I was blown away by these creations. I actually really like them, particularly this perpetual machine that picks a ducky and puts it on.
Yes, the Ducks Unlimited, yes.
So feedbackcontrol.com, of course, there will be a link in the description. Yeah, go and check it out. There's plenty of mechatronic art, as Jeff mentioned. It's funny also that you mentioned that you follow the path of least dislikeness, or I don't know how to call it, but that's essentially my story too, in a certain sense. And then I found myself quite fascinated by this theory of everything that applies to every domain, and it's very clean and elegant and allows you to say so many things. But yeah, so maybe going back to your own personal story, Mike Athans, I'd be curious actually in our audience how many know the name, but he's one of the most influential figures in 20th century control systems, arguably, longtime MIT professor, known for modern optimal control, stochastic control, decentralized control, but perhaps most famously gains scheduling and a multivariable robust control. So, and here is actually where you come in, right? Can you tell me a bit about the backstory of your PhD thesis and how it all started?
So one thing about Mike Athans, just to add to your kind comments, is that, the name of the lab, which is still the name of the lab, was Information and Decision Systems. And it was something that I appreciated later on. It was not I think that lab used to be called Servo Mechanisms Laboratory. It might have had other names as well. But one of the things where I think he was very visionary is recognizing that controls and systems is broadly applicable. It's not just about getting a motor to spin at a certain speed, but if you look at the names of information and decisions, that controls is relevant. And now I think this is widely recognized. It's been recognized for a while, and like the recent article and monograph on control for societal impact, cyber-physical human systems, this is recognized. But I think that he was very early on in, say, mid-70s in kind of seeing that systems theory and feedback control as broadly relevant to things outside of the traditionally recognized applications.
If I'm not mistaken, it was him actually changing the name, right? From the previous name to the current name, right?
I believe so.
Okay.
And so with gain scheduling, he took me on as a PhD student, and his style is very hands-off, actually. And I find myself in the same way that, as you mentioned, you're a parent and we're parents, and we find ourselves saying things that our parents said and not thinking that we're going to say it. But that's just, we inherit certain attitudes. So his style is more as he didn't say this, but essentially his spirit was that I'm an advisor, not a supervisor. And that here's some directions that we can take, and which one do you find appealing? And every few weeks I would go to him and say, this is what I'm thinking about. And he would offer some ideas. And was otherwise kind of kind of left a lot of autonomy to his advisees. So he kind of mentioned a few ideas. Curiously, one of them was about distributed decision-making, which I didn't pick up at the time. But then the other one was the idea of gain scheduling. So at the time, gain scheduling, let me back up a bit. It's kind of typical that, say, ideas in academia mature and then they move along what they call these technology readiness levels, where as they become ready to be applied research and then or proof of concept and then tested. But with gain scheduling, it was the reverse, that you had that pretty much everything that flew or swam was using gain scheduling. And the theory behind gain scheduling had yet to be kind of developed. And so that was pretty much the genesis of this direction. Saying gain scheduling is something that works, and there's some heuristics on when it'll work, and can we kind of investigate these heuristics and see what's behind it, and with the potential of going forward and having it more of a rigorous design methodology.
To me, it was quite surprising actually to learn that up until then, there was no theory about I mean, it looks like gain scheduling to me is one of those methods that is, I don't know how to say it better, but I would argue it's one of those methods that is very much used in practice, just like MPC or PID. They really, it's something that a practitioner will use, not to say anything negative about the academic world, but at the end of the day, all that we produce essentially boils down to a handful of methods that are actually applied in the real world. And to learn that, I guess here we are around late 1980s.
That's right. That's right.
Until then, there was no solid theory except for a few publications about the method, which is somehow similar also to the story of model predictive control in a sense, because it started in the chemical process industry and then slowly it moved into the academic circles, and the academics figured out how it was working. And I guess you were at the forefront of providing rigorous foundations for gain scheduling, right? And maybe actually we should back it off and say, what is gain scheduling?
Yes. There's a lot of course, classical control deals with linear systems, and linear systems work well as an approximation to nonlinear systems, but of course it's a local approximation. So the idea behind gain scheduling, if we take flight control as an example, a aircraft can fly through many domains of high altitude, low altitude, high velocity, low velocity, different types of angles. And around each domain, they call it the flight envelope, one can construct a linear system that approximates the behavior and then rely on very well-developed linear tools to design a controller at that point in the operating envelope. But what happens now when there's movement between these points in the operating envelope? Well, a natural idea would be that I know what to do at point A, I know what to do at point B, so let me just interpolate in between them and hope for the best. And the hope for the best part comes in when there's kind of aggressive transitions from A to B. If it's lingering at A and lingering at B, pretty much things will work. But what happens when it becomes more aggressive? And so that's the gain scheduling. The gain refers to the linear controller that was designed, and then the scheduling is the interpolation part. And and that's gain scheduling in a nutshell. So it's a very natural idea given the prevalence of linear ideas or linear methodologies, and just how do we translate those to nonlinear in a way that kind of preserves or tries to have the best of both worlds of the linear insights, the power of linear tools, but a bit placed outside of their intended utilization in a nonlinear setting.
Yeah, indeed. And so just to try and set the stage also, or context for the audience, as we say, so you start your research in the late 80s, approaching the first years of the 90s. So that is actually the, let's say, end of the golden age of robustness, I would say, in controls. So H-infinity methods and all of that. I think LMIs were probably starting to surface around that time, or the use of LMIs starting to surface at that time. And again, scheduling, or at least in the way I picture it in my brain, is essentially writing down a classical linear time invariant system in state space form. I wonder whether there was an input-output formulation as well prior to that, but in state space form, where now the matrices, so ABCD matrices that classically define our favorite linear time invariant system, depend on a parameter, or better, a scheduling variable, theta, that is some sort of signal that determines what are these matrices. And typically, as you say, that theta varies slowly, just like you were mentioning before, the angle of attack of a certain jet plane, or and the examples that come to mind are those in aerospace. And so maybe you can tell us about how does it happen that one formalizes something that exists in practice and you want to turn into theory.
So you take a hypothetical gain schedule design, and so it typically involves a linearization, a design, and then the scheduling part. And now you have this indexed collection of designs. But the indexed collection of designs, then you translate that back to what is this as an overall nonlinear system? Because at the end of the day, once you do the scheduling and have that feedback, you have a nonlinear system that's tied together, and ask what will it take for this nonlinear system to be stable, to have good disturbance rejection, to have good robustness, etc. And so this form emerges, and essentially it becomes like you're analyzing, it's still, one can get away with analyzing linear systems, but they end up being linear time varying systems. Now, that was the kind of the emergence of this middle ground. To understand nonlinear gain schedule systems was to understand a certain family of time varying systems. And this is where the paradigm of linear parameter varying systems came out, so-called LPV systems. And so, yes, it's just time varying systems, but there's a difference in the spirit of questions. So one is, I'm not asking is a specific time trajectory, time varying system stable, but rather a family. This is the kinds of time variations we can experience. When is this family stable? And likewise, I'm not asking, how do I design a controller for one fixed value of this parameter, but rather for a family of values. For a family of values and a family of dynamic behaviors. Is it moving slowly? Is it moving quickly? Is it switching systems? And it turned out that the framework of LPV, it kind of emerged from, the terminology emerged from my thesis. And actually, I want a little backstory there. It was a time where, marketing was very important, and you needed a catchy acronym. Okay. So there was robust control, there was mu synthesis, whatever mu is, it's just a Greek letter. But you got to have, like you referred to LMIs, you got to have a catchy term to describe that direction. So LPV was not a term before my thesis, and it became a term, and it caught on largely, okay, maybe my thesis got that terminology started, but largely, as you mentioned, because of the very rapid advancements in LMI approaches. It translated beautifully to that, and it's mostly the work of others that said, now this is going to be a bunch of letters to reflect the importance of marketing. The LMI approach to LPV systems. And it became widely successful that these various robust control design methods could, with some kind of simple modifications, and also the advances in convex optimization brought it all together. And so now one can have a very structured way to design LPV gain scheduled systems, which then translated to certain nonlinear gain scheduled systems as well. So all of that, as you pointed out, came together nicely. And that goes back to fishing and luck. You can have these same ideas at a different point in time, and maybe they wouldn't come together in the way that they did.
It really means a lot to be the right person at the right time, and the right background. I'm glad that you actually mentioned the LPV terminology story, because you anticipated one of my questions. I was trying to understand what is the difference between a gain schedule system and linear parameter varying. Of course, the subject, I would say, is still in vogue today because it has a lot of connections, and it somehow carried a lot of connections also throughout the history, to the current history, I would say, of controls. I can think of many connections, like, as you say, switching systems. In my own personal experience, even contraction, because in one way or another, contraction looks at families of linearizations of nonlinear systems. And
absolutely, yes.
That's one way to think about the problem. And so it looks like it's going to be lasting again for
a bit longer,
for a while as a paradigm. I'm also glad that you mentioned the connection to LMIs. Maybe we can even spend a few words about what is this connection, if you like, and what does it mean to do design with a linear parameter varying system, which is, as you say, is a linear time varying system, which means it's a linear system where, if we think about a classical state space form, the matrices that describe the dynamics of the system are possibly time varying. And we know that in those families of systems, weird things can happen. For example, you have, I should mention, we haven't mentioned any article yet, and I think I would like to point the readers to, not the readers, the audience, to reading actually some of these papers. You have an overview of linear parameter varying systems. This is a book chapter in collection of articles on linear parameter varying systems from 2012. I guess also research on gain scheduling written with Wilson Roque as well, just for the audience to understand, like if they want to start somewhere with this family of systems. And as I mentioned, weird things can happen. There's one example that I was reading in one of these two articles in your PhD thesis, where you show that there's a system that is always stable. So for every t, the A matrix is stable, but you can actually generate trajectories that spiral out away from the origin, showing that the behaviors that these systems can generate are quite rich. And so why is it that, somehow complicating our life leads to tractable designs, for example, through LMIs?
So there's two parts. So first of all, these kind of examples actually date back to ODE papers in the 60s and maybe even earlier of you can have something that frozen in time has nice eigenvalues, but overall is unstable. And the opposite, by the way, of something that has unstable eigenvalues, but frozen in time, but as a time-varying system, it's stable. There is a physical way one can think about this, is like, you can imagine some kind of an oscillator, like a spring, and a mass in a spring. And then when it's expanding, the spring is loose. And when it's contracting, the spring switches to being stiff. So it's going to come in a lot faster than it went out.
Yeah.
And then now it expands again and it goes out even farther, and then it becomes stiff again and then loose again and stiff again. And through this kind of switching system, you can get instability, whereas if it was a single spring, it would always have been stable. And so the connection to LMIs, you can say that LMIs are like the search for quadratic looking Lyapunov functions. And the connection there is that one can just write several conditions saying, for this system to be stable, we need a family of, or we conjecture a particular Lyapunov function that will be the certificate. And this Lyapunov function will work if this set of linear matrix inequalities has a solution. And then that can turn into a design tool as well, where you embed into the LMIs the to-be designed parameters of a gain schedule controller. Now, there is a limitation to that. And this is kind of something that happens in many areas. You impose a structure of a Lyapunov function, a proposed Lyapunov function, and hope for the best. And if it works, great. If it doesn't work, that means that my proposed structure didn't work, but maybe there's a different Lyapunov function out there that would have been better. And actually, there's always a Lyapunov function out there that would be better for switch systems or LPV systems. The problem is that they're not quadratic. And so the search for these Lyapunov functions, and we did do some work on trying to kind of construct them, but they're not really numerically attractive. But there's always a Lyapunov function out there that will certify stability if there is stability, and that can be used for certain types of designs. But you don't have the computational attractiveness of the linear matrix inequality or the LMI formulation. And so it's all in the time domain. And the playbook is impose a structure on a Lyapunov function that's going to serve as a certificate. If all of these LMIs work out, then we're done. If they don't work out, well, better luck next time.
Yeah, and also, the fact, maybe we should mention to some of our audience that may not be familiar with other episodes that we've had in the past, the fact that you can design through LMIs or analyze these systems through LMIs then allows you also to connect to frequency domain interpretations as well. So that's also one of the powerful, let's say, connections that LMIs allow you to make. I was just wondering, I have two follow-up questions on this subject, and then if you, I don't know, depending on whether you...
I want to comment on what you said when you said frequency domain.
Yeah.
So that they really don't carry over to time-varying systems.
Oh, yeah.
But they do carry over to asking things like, what is going to be the optimal controller that minimizes the gain?
Yeah.
Like optimal disturbance rejection. Optimal disturbance rejection can be formulated in the time domain or in the frequency domain. And for time invariant systems, one has a choice. But for time varying systems, there is no choice. But the LMIs that emerge can have that, as you pointed out, the dual interpretation if it's a time invariant system. But for time varying systems, it's, the frequency domain interpretation is lost.
You're right. In fact, I'm looking forward to asking you a bunch of questions about the ensuing papers that you've written about the necessity of the small gain theorem. I was blown away by a big fan of those papers that I hadn't read before. They don't really have that many citations, and in my view, they should have many more. But anyways, before we move into that, I wanted to ask you, well, two things. One is, okay, what do we have to learn here in the sense that, so gain schedule worked already in industry long before theory caught up. So is there a lesson to be learned by control theorists out there from this episode, and also from MPC, and also from PAD? And second, maybe it's complementary also to this question, what did LPV theory make precise that gain scheduling left informal? One of these things, as you mentioned also in another paper, is schedule on a slow variable, for example. This is called Gain Scheduling Potential Hazards and Possible Remedies on the Control Systems magazine.
So starting with the second question, scheduling on a slow variable, as we talked about earlier, there's this phenomenon that a system, if frozen in frozen parameters, is stable, but as the parameters vary in time, it can become unstable. But if variations are slow, and again, this goes back to classical results on ODEs in the 60s, if the variations are slow, then the stability is preserved. And so what the LPV/LMI approach allowed is not just inheriting the whatever it is, but rather designing for variations in advance. Say we anticipate that this is going to be the speed of variations in advance, and now let's look for a controller that can accommodate, if it exists, and that can accommodate that speed. So it's flipped it from inheriting it is what it is to let's design for a certain capability. And that was captured formally in the linear matrix inequalities associated with LPV systems. And then another part that the analysis showed is that it showed exactly what was the time varying system to be analyzed. And it turns out it's not necessarily the one that comes in contractive analysis of linearization around trajectories. And it's not even the family of linear systems where you linearize at different operating conditions. Rather, after you do the transformation, there's this new system that emerges that was not on the table for analysis. And that is the LPV system that needs to be analyzed. So it actually revealed what was the essential underlying driver of stability and performance. So that, as we pointed out, the scheduling variable is typically an endogenous variable. It can be modeled as an exogenous, as coming from wherever, but actually it is internal. So what would be an example of that? Let's take, for example, altitude. Is altitude external to an aircraft or internal to an aircraft? We can model it as external, but ultimately the altitude emerges from the maneuvers of the aircraft. So it's really internal. And so then the terminology quasi-LPV was introduced to saying that it looks like an LPV system, but this parameter is really one of the state variables. And whether or not we choose to leverage that in the analysis and design is to be determined. So it made very precise what is the underlying system that maps to an LPV system that needs to be analyzed. As for the previous part of a lesson learned, it's not unique to controls. And there's always this cycle, I think in design circles, they call it the design spiral of something, you can ask, was applications ahead of theory in the case of gate scheduling? Let's say the answer is yes. But remember, those applications were using linear systems approaches that came out of, say, or were addressed by academia as well. So where is the chicken and egg in all of this discussion? It's all part of a big cycle. So yes, one can argue that's what determines when the cycle turns from industry to academia. And a lot of the times it's other kind of technologies. So one example would be MPC with its focus on the, say, in the chemical processes industry. And then computation allowed things to be optimization to turn into a real-time activity, which meant that MPC can now try to address systems with much more faster timescales. And now we see MPC for flight control and at that timescale. But it was a different technology that was outside of controls that made us ask, well, now it's time to revisit MPC in a way that it wasn't really being considered before. And you can say maybe as we said, there was this nice convergence of the results from robust control and convex optimization that enabled revisiting certain approaches. So it's a common cycle. And, that's, if we broaden the discussion to just controls, there's they're very nice set of slides. You can see them online by Carl Astrom on the history of controls. And, it goes back to water clocks and BC times. And it's actually very encouraging that the concept of feedback is almost timeless, because there's going to be new sensors, new actuation, new data, new online, new communication capabilities, new computational capabilities, which allows us to close new feedback loops that we couldn't close before, which makes us ask different questions about feedback systems and control systems. And so it's part of it is the back and forth between industry and academia, but a big part of it is, let's call it third-party advances that feed into that discussion.
You're bringing out so many talking points that we're gonna spend the whole episode just about your PhD. So, well, okay, I must comment on a couple of things you mentioned. So the first one is related to this tension and this cycle that tends to be present and come back over and over. I had a conversation some time ago, actually, with Manfred Morari in talking about MPC and its history, but also outside, let's say, of the episode. And what struck me in this conversation was when he said, you need a gradient, essentially, between academia and industry. And this gradient is beneficial because it creates somehow dynamics of ideas, which makes a lot of sense to me. And it seems to be the case also in this context. And the other one, as you say, about this third party and the generation of new technologies, new sensors, new actuators, essentially gives us, or at least makes me feel very, very positive about my own field, in spite of the so many that keep on saying that, control is dead. And I hear it over and over from people that I tend to interview on this show, that control has been dead since maybe 40 years or something, according to some. But it cannot be more alive than it is, in my own perception. There's so many things to be excited about. Synthetic biology, games that we're going to discuss today, hopefully humans in the loop, algorithms in the loop. So it brings me a lot of hope, let's say.
Yeah, no, I like the positivity and the optimism of this interaction. Let me bring it down a little bit. So my first, I won't say where, but my first interview for an academic position, I get off the plane and my host is telling me how controls is dead. And then the interview went down from there. So yeah, it's been dead for a while. But it's the notion of, I think, feedback and its implications it has been a timeless one. Yeah. Now, I do think, and maybe we'll touch on this later, is that we are entering a paradigm shift in the world of, say, controls. And my source of optimism here, as compared to you, is that I don't have to figure it out for many more years, whereas you do, as in this stage of your career. If you take something like gain scheduling or various methodologies for designing controllers, if you look at there are all these special forms in nonlinear controllers that if it looks like this, we know what to do. If it looks like that, we know what to do. But now with the computation and data-driven design, it's very different in that we don't have to put in a lot of effort necessarily to make a system look a certain way so we'll even have a chance of knowing when to start. So it's really changed the rules for at least designing controllers. And it's something that I'm trying to come to terms with, of what are the implications going forward for the field. I'm not going to add my name to the controls is dead community, but there has been a paradigm shift for sure. And the next few years is going to look very different. And I think this is going to impact research, but also instruction and I say this, our department, it has a history. It was once called industrial engineering was part of mechanical, and then this was called general engineering. And there is a lot of controls in general engineering. It's probably one of the few departments, if only, maybe the only department that has 2 required undergraduate controls classes, and as required for the systems engineering degree. And I'm teaching the state space version of the second required controls class, and I'm thinking that students are watching videos of robot dogs doing backflips, and should I be asking them to check the condition of a controllability Gramian? and what am I trying to do here? I think it's really bringing in challenges to the research and also challenges to education. We got to rethink pretty much everything of what do we teach and how do we teach it.
So I'm very tempted to pick you up on this comment too, but this is something that I would envision for the end of the episode, not for the
okay
for the middle. I mean, I have lots to say about what you just mentioned, and I think you're bringing up excellent points, both, and as you say, at the educational and pedagogical level. There's also a culture shift in terms of how we do research. Machine learning is clearly taking the stage in terms of, rather than producing theorems, we produce tables with performance, and that's what we care about, or videos. But at the same time, I don't know, what brings me hope is comments like those from Alberto San Giovanni Vincentelli, who was also on the podcast, who says focus on the fundamentals, because the fundamentals are actually what your Swiss knife that you use in your everyday when there's something new to solve. So my hope is that there's some smart kids out there that are not hypnotized by some trends and will focus on the fundamentals nonetheless, and carry the torch for the future generations, hopefully. But I'm very glad to expand on this, maybe towards the end.
Okay.
I think we could try to move on from your PhD, since we are now at minute 43. So one thing that actually struck me in reading about your journey and your academic career is that you moved a lot, also geographically speaking. So after MIT, you moved to Minnesota, then to Texas, then to California. You worked with some other very bright minds, or some that I respect a lot, including Munzet Ale. I wonder, what was your subjective experience in those years of transition, let's say, where you moved on? Of course, you built on the theory of linear parameter varying systems, and then you gradually started broadening your horizons.
Yeah, so I was very fortunate to work with Mike Athans as my PhD advisor, and then to be exposed at the culture at LIDS, to see people who were like Sanjoy Mitter, who were perceived as very senior at the time, and he was, but to see his kind of his boundless curiosity of someone in his position, director of the lab, who would just roam the halls and say, what's going on? And was always ready for a chat that follows a kind of an academic leisure. I think it's a time and a philosophy that's lost. We're always busy and setting up appointments. But he would just stroll and say, what's up, and what are you working on? And then to get exposed to Munzer Dalhi joined LIDS the last year of my PhD, and then he and Sanjoy Mitter were my postdoctoral advisors. And to see their style, and it was also kind of a very influential on me for a career of saying this is how, like an approach to ask questions. This is an approach what to do when you get stuck, why get stuck. He was there. Kameshwar Pula also was very influential for me in those years as well. And these have become lifelong, what started off as mentorships as lifelong engagements and relations. I'll start with Minnesota as well. So in Minnesota, I land next door to Trifon Giorgio and Ellen Tannenbaum. And with Trifon, I know he's been on your podcast. I referenced Trifon, not necessarily by name. So now as a department head, we started a mentorship arrangement in the department. But I mentioned that you can have a mentorship program without mentorship, and you can have mentorship without a program. And that it's really about the culture. And Trifon, I don't think we've written a paper together, but I had more technical conversations with him than anyone for the first few years of just this idea of just sitting and talking about ideas. And again, goes back to academic leisure, which is sort of lost in the current kind of culture of academia. And that had a lifelong impact on me as well. In terms of moving around, I'd like to give you a comment beyond short attention span. Or, Minnesota was too cold and Texas was too hot and LA was too cool. But, each move had its appeal at the time, and we can look back in life and say, did I do this or that for the right reasons or the wrong reasons? One lesson learned that I will emphasize is to not take for granted a very supportive environment with colleagues whose presence you enjoy. It's not something that you'll find anywhere. And, I found it to various degrees here and there, but it's something that is actually very precious when you find it. And again, it's one of these life lessons that are appreciated later on in retrospect. Yeah.
Amen.
Yeah.
So I can also personally relate to what you just said, actually. So I had the same experience in some places that I visited. I think it would be inelegant given that it was not very long ago, but some places where I've been incredible from that perspective. And the mentorship and the presence of some people in particular is just their presence makes a huge difference, as you say. Of course, we can go chronologically or thematically. I feel that in the 90s, your focus becomes robust control, nonlinear time-varying systems. And well, if you could comment on a couple of papers that I really enjoyed. So one of them is called The Necessity of the Small Gain Theorem for Time-Varying and Nonlinear Systems. And the other one is Performance Limitations in Sensitivity Reduction for Nonlinear Plants. Both of them are true gems. From my perspective, they're very, very short and punchy. Well, at least one of them is short and punchy, but it gives a very, very nice account of the waterbed effect in a nonlinear world. Now, we're going to elaborate on this, I guess.
Okay, so if we go to the small gain theorem, the necessity, so there was classic work in the 60s by Zames and also by Sandberg, both of whom I got to meet in different stages of my career at those days. It's a sufficient condition to analyze stability of a nonlinear interaction. Of course, with nonlinear systems, we don't have the luxury of looking at eigenvalues. And also, we want to not just analyze the stability of a specific system, but for families of systems. And so you look at high-level properties and say, if they have these properties, then we can make certain conclusions. So the small gain theorem said that if the amplification around the loop is less than 1, then it's stable. That was the sufficiency. Now, the necessity would be, what if it's bigger than 1? What if the amplification is bigger than 1? And then that paper showed that for a particular class of nonlinear systems, in particular fading memory systems, I can say what that is in a bit, that the loop gain has to be less than 1 for it to be stable for an entire family of such systems. And so it's these kind of necessary and sufficient ideas are out there. Let me give an example. Say for linear systems, if they have a quadratic Lyapunov function, then you can certify stability. And if it's stable, well, there is a quadratic Lyapunov function out there. It's necessary. For time-varying systems or switching systems, that's not the case. If I have a quadratic Lyapunov function, great, you can certify stability. But if a switching system is stable, that doesn't mean that that there's a quadratic Lyapunov function out there. For this, it provided a very tight condition that if the gain is less than 1, it's stable. But if the gain is not less than 1, then you can construct situations where it goes unstable. So the less than 1 was necessary as well to be stable for a family of perturbations. Now, where does family perturbations come from? The small gain theorem is set up to analyze robustness. I want to make sure that not just my specific system is stable, but there's an entire family with a specific, a certain characterization. And I want all of them to be stable. And the small gain condition said, if this happens, then all of them will be stable. And then if it's violated, what we showed is that one of them, you can always find one of them where it won't be stable. So that was the necessity part. It was for fading memory nonlinear systems. And so fading memory means the impact of an input eventually is forgotten. If you wait long enough, it's as though you're starting from scratch. And that's important because imagine you have a nonlinear system that says, okay, as I'm perturbed for a while, I'm just going to shut off. And I'm not going to do anything forever on. So the gain becomes 0, essentially, in the long run, where it wasn't 0 in the short run. So, yeah, imagine if there's a system that you could offend. Okay, so once the system is offended, it's not going to deal with you anymore. That's not fading memory. Okay, so fading memory means if you wait long enough, the system will no longer be offended by what you did.
It's a benevolent system.
Yes. Okay, it's forgiving. Mm-hmm. And that's what the fading memory part is. If it's not fading memory, you couldn't reach these sort of conclusions. So for me, that was kind of a dream project in that in getting into gain scheduling, you look at stability analysis of nonlinear systems from a Lyapunov perspective and also from an input-output perspective. And there are a couple of books that I was carrying around with me incessantly. There's a very classic book by Desor and Vidyasagar, and then also a nonlinear systems book by Vidyasagar.
2 jewels, both of them.
Yes. And they have one of the most important characteristics of really great books is that they're short. Okay, and they didn't try to be comprehensive. They say the authors took a stand, and this is a set of material that we think is essential, versus trying to be comprehensive to have something in there for everybody. And so to be able to kind of take what were results that had been around for decades and say, yes, this was an open question about them. The necessity was understood for linear systems with linear perturbations. But to extend it to nonlinear systems with nonlinear perturbations was also just kind of personally rewarding as someone who was a big fan of those jewels of books.
I'm sure also in reading this specific publication, okay, maybe we should also give it full credit. It's called The Necessity of the Small Gain Theorem for Time-Varying and Nonlinear Systems on Transactions of Automatic Control. It's a single author paper by you. In reading this particular paper, I was blown away in different directions, let's say. So first of all, because of course, it's related to your trajectory and your also previous work, but somehow you were broadening quite a bit the perspective and also the set of tools that you were using. You were also on top of, let's say, the modern trends, I guess, at the time, because 1991 was the inception of, I would say, a golden age of nonlinear control, or definitely it was the right time to write about these subjects. And the third element that I found particularly interesting was the fading memory property that keeps on or bouncing, let's say, in front of me in my own academic journey. I haven't used it myself, but I've seen many, many people excited about it for different reasons. Starting with, of course, Stephen Boyd's publication with Leon Chua, the fading memory and the problem of approximating nonlinear operators with Volterra series. And this idea of forgetting the initial condition happens to be central also in contraction theory and also in trying to somehow resurrect also this input-output perspective to complement some of the existing methods that are more state-spaced. So I really enjoyed this publication very much.
Thanks.
And the second one was the performance limitations and sensitivity reduction for nonlinear plans. What's that about, actually?
So, so as you pointed out, it's kind of hasn't received that many citations, and I did my best to give it a title to make sure that would be the case. Apparently, because that title, in retrospect, just doesn't reflect the excitement that I had about that.
Should be called the nonlinear waterbed effect.
A waterbed effect, yeah. So if to back up, there's a waterbed effect that's recognized with linear systems.
Yeah.
And the idea is as follows, is that any performance comes at a cost. And so if we're able to reject disturbances, for example, in a particular frequency range, the better we reject those disturbances, then the worse we reject those disturbances in a different frequency range. Mm-hmm. And then if you want to say, well, I don't have any disturbances in that other frequency ranges, and then you can change the topic to say, the closer I am to instability, the less, so the better performance I have, the closer I am to instability under other types of perturbations. And, you could see this anecdotally in life of you're riding a bicycle at a slow speed, at a reasonable speed, and you're not going to fall if a little bit of dirt or sand on the sidewalk is not going to impact you. But at a high speed, then we become sensitive to those sorts of perturbations. Okay? So there's sort of a robustness versus performance trade-off is present conversationally, and it was also quantitatively. And there was some work at the time actually it's classical work from the Bodhi era, but then modern work for multivariable systems by Fudenberg and Luz kind of captured this as well, that if you have non-minimum phase systems, which is a particular category of systems that have been known to be difficult to control, that you're going to have this waterbed effect. It's been called waterbed effect, it's been called push-pop. It was referenced actually to very dramatically in the very first Bodhi lecture by Gunther Stein. He called it the conservation of dirt. And the dirt was, if you remove dirt from one location, you got to put it somewhere else. And then he had a very nice graphic to illustrate that as well. And so these phenomena were there. But then you can ask the question, well, what if I use nonlinear controllers? And are we still subject to that, those sorts of trade-offs? And not just nonlinear controllers for linear systems, but can nonlinear systems also have this? Well, first of all, what is a non-minimum phase nonlinear system? Because nonlinear systems don't have transfer functions. So how would you describe it? But even if we're not interested in analyzing nonlinear systems, can I use nonlinear controllers to get around this performance trade-off? I think that question is actually current, in the sense that, okay, I'm going to use whatever, machine learning, deep learning, you name it, to design a nonlinear controller, and it's going to perform better than linear controllers. Yes, well, it better. But does it bypass these sort of trade-offs? And it doesn't matter how sophisticated your control design method is, these trade-offs prevail. And so it was able to reach that conclusion. It was able to define what is a non-minimum phase nonlinear system in a way that was not popular at the time or currently. And it was able to say that, yes, you still have this trade-off even if you're using nonlinear controllers. And the main leverage was just one of causality, that if you're using a controller that can't tell the future, then that was it. That was pretty much the essential assumption on the controller. You have a controller that can't tell the future, and these trade-offs will be there as long as that's the case.
This is so fascinating.
And so, yeah, that was the result at the time. And then there were other folks that kind of took it beyond sensitivity minimization or disturbance rejection to other frameworks as well. And so that work had been extended by a couple of folks in the following years. I think Saron and Goodwin had actually turned a few papers in a monograph that built on that.
I did see that, actually. I was wondering whether there was a connection. I just want to try to do justice even more so for like the broader audiences. And I also have a couple of technical questions related to that paper. Mm-hmm. First of all, it takes as you say, a functional analytic approach to trying to an input-output perspective, let's say, to address this question of the waterbed effect or the conservation of dirt, which, by the way, whoever hasn't seen the Gunther Stein lecture, they should. I've already advertised it multiple times in this podcast. Carl Johan Ostrom says that it's like red wine. It gets better as it ages. And I think it's true. And as you say, there's this iconic plot where there's a person shoveling dirt from low frequency to high frequency, showing the plot of the sensitivity function of this closed loop. And the body integral says that the area under this curve is preserved. So however you design your controller, if you remove dirt from low frequency, you will have more dirt at high frequency. And so there will be frequencies whereby you will be destabilized. So you mentioned that the non-minimum phase condition does not have, or let's say the zero dynamics does not have a counterpart in the nonlinear world. But having spent some time with Alessandro Astolfi, I think there is indeed some sort of notion if you take a differential geometric approach to nonlinear systems. And I was curious whether anybody has tried to make a connection, let's say, between this particular result that you show, taking an input-output perspective with those tools.
So our notion of non-minimum phaselessness was that actually it stemmed from work of Vidya Sagar that talked about, it's a bit technical, about the graph of a system. So what's the graph of a system? If there are certain trajectories that can be produced by a dynamical system, and you can ask the question, what does it take to produce these trajectories? What do I have to inject for this behavior to appear? And non-minimum phaseness was that for certain behaviors require an unbounded input, an unstable input. That if I wanted a certain behavior to come out of a system, then what was driving the system has to be a signal that's blowing up. And if that's the case, that's called non-minimum phase. That was the non-minimum phaseness that we used, that there are certain things that cannot be done unless we're going to excite the system with a unbounded control excitement. And so in a stable system, we're not allowed to use unbounded excitation. And so it was really an input-output perspective that didn't rely on the nonlinear representation and the zero dynamics. I think there is a connection. Please work it out and let me know what that is, because it's something that I've been curious about. I haven't
problem for the young guns.
Yeah, I haven't acted on it. I'm sure there's a connection. It may have been resolved by someone somewhere. I haven't followed up on it, and actually it was the part of that is deliberate, to try to kind of have a characterization that's not dependent on a representation. To say that I don't need a state space model to define this and to define non-minimum phasedness. And so each one has its own value, and I'm fine with that. And what's the connection? I'm curious, but haven't acted on that. Yeah.
So let me advertise and do justice also to this paper, which in my view should have a bit more attention. It's on the system and control letters, 1991, performance limitations in sensitivity reduction for nonlinear plants. Yes, I think these two papers are, in a sense, representative of another phase of your academic journey, where you focus, as you say, on robustability, time-bearing uncertainty, nonlinear control, even safe control, or it wasn't called that way at the time. It was called constrained control and even set-valued observers. I don't know whether you have a favorite application coming out of that stream of research.
So where that was coming from is that there were certain ideas in linear robust control, and as you said, there was this kind of a golden age of the robust control in the late 80s, and now we're moving into the 90s, which was a time of rapid development of nonlinear systems. What we'd like to see, are there things that are analogous? And so the small gain condition necessity was analogous. The waterbed effect was analogous. There are other questions that but there are also questions like, what is the role of nonlinear control design, even for linear systems? Can nonlinear controllers do things that linear controllers can't do? And so there was a set of results there, people asking the questions, and sometimes the answer is yes, sometimes the answer was no, that you didn't have to look at nonlinear controllers to achieve things that linear controllers couldn't do. So one of the questions that people asked, and this was stemming from a paper of Venkatesh Salagrama and Munzer Dali, in control systems, if you have access to the state, you never build an observer. okay, that I don't need to have an observer because I'm measuring everything of relevance. And now there is a particular optimal control that they were investigating, so-called L1 optimal control. And that paper showed that if you have access to the state, the optimal controller actually is a dynamic controller and its order can be arbitrarily high, which was very different from all other linear optimal controllers. In particular, if you had the state, you never had to have any dynamics in your controller. The controller was just a linear memoryless function of the state. So then we looked at that and then saw that actually, yes, the optimal linear controller is dynamic, but if you're allowed to use nonlinear controllers, you don't need to build an observer again. It is actually a static function of the state. No dynamics are needed, but you have to pay the price that it's a nonlinear controller. So it's not so much that nonlinear control can do something that linear control can't, but rather the structure was different. I don't need an observer if I'm allowed to use a nonlinear controller. And then there were methods to try to build that nonlinear controller. And like everything new, it wasn't. You can find kind of references or similar ideas in a variety of prior work in the 70s in particular. And it goes back to luck and computation, that some ideas are good ideas, but they just can't be implemented to be appreciated. So there are these recursive methods that you find them in the controls world. You find them now being just a whole variety of ways to reach the same conclusions, whether it's Hamilton-Jacobi-Bellman approach or control barrier set approach. Actually, there's a handful of different approaches, safety filters approach. But all of them are trying to kind of do the same thing, of guarantee that the system state does not exceed certain boundaries. And there is a universal approach. And when something is universal, that's always double-edged. It's universal means that, okay, it always works. So you got to pay, back to waterbed effect, you got to pay for it somewhere. And there where you pay for it is in computations. But there's also, it goes back to verification and from a computer science community as well, of just understanding when can be a system controlled to keep its operations within a certain desired range. And there are universal algorithms out there. I think this also evolved into explicit MPC as another kind of a perspective on similar ideas. And when the computation is around, then one can start computing controllers, constructing controllers, and it's always going to be kind of a computationally disadvantaged, but that doesn't make it useless. For low order systems, it can be done. And what's low order is a function of time, because the computational capabilities means that we can address higher and higher order systems to some limits. Yeah, that emerged out of asking what can nonlinear control do that linear control couldn't do. Then that also was developed for LPV systems and to construct nonlinear controls for LPV systems. And then now what happens if you don't have access to the state? Then you need to build an observer. And it turns out that the observers for those systems look very different than what are typical observers, say like Leuenberger observer. Rather, they're so-called set-valued observers, where based on a model and based on data, you have a set-valued solution. This is where I think the state could be. And now if I'm going to have a control, it has to work for all of the possibilities. And again, it's a universal structure. Whether or not you can construct anything is a separate question.
This is very, very cool. I can think of many papers that I've read in preparing this episode. One of them was set-valued observers and optimal disturbance rejection, but there's many others with KY2, so approximate set-valued observers for nonlinear systems. Also, other complementary papers that I found very cute in a sense, like linear non-quadratic optimal control, where you keep the linear dynamics, but you ask the question, what happens when I change the objective? Yeah, so generally, I could consider these as ancestors of approach. Well, I don't know whether they were there at the time. They were probably surfacing, I guess. So hybrid systems and differential inclusions being used in the context of controls.
Yeah, this kind of a set valued perspective of a set valued in it could be with differential inclusions, the set of possible right-hand sides to the model is one perspective as well. Yeah, and so there is a mathematical theory, and the connection has been made of so-called viability theory that made that connection from the math and differential equations world, and then it found its way into the controls world as well.
So even in terms of tools, you were quite eclectic in a certain sense. You started from game scheduling, then you moved on to very functional analytic approaches, then hardcore, as you say, viability theory, so hardcore analysis tools. And then next is a new phase that, again, radically different compared to what we have seen until now. So I guess here, I mean, it's something that I struggled to understand in a certain sense, looking at the records somehow. So how does the interest in game theory and decentralized control surface? We're around the year 2000, more or less, well, a bit more than that. And geographically, I lost track of where you were. I think you were in LA at the time.
This UCLA days, yes.
Yeah, okay. And so you're very well known also outside of the controls community about the work you've done in game theory in the last, I would say, well, starting from the years 2000, more or less. So I'm curious about how do I reconcile the two Jeffs, the pre-2000, after 2000?
Okay, so there was a bridge, but let me first talk about the kind of the setting. At the time, and this continues to be an area of interest, there was interest in autonomous systems, and the ratios were such that, say, for an autonomous aircraft, it's actually semi-autonomous in that there's a remote pilot, and you might have many pilots for one aircraft. And then how do you reverse that ratio and say have one pilot for multiple aircrafts? And so you can think of that in the same way as a coach and a team, and say in a team sport, there's a difference between, say, a coach controlling each player like a marionette, like a grand puppeteer, versus a coach giving high-level kind of plans, and whereas the individual players have to execute real time. And when individual players are executing real time, also some players are aware of things that other players aren't aware of. There's opportunities for miscoordination. When the times that we've played team sports, you can like pass the ball to someone thinking they're going to run, but they don't run. That wouldn't happen if it's going to be like one person controlling everyone. You can find a video online of multi-million-dollar athletes dropping a ball because all of them ran to catch the ball, but then they all stopped thinking the other one is going to catch the ball. And each one of them alone could have caught the ball, but together they were unable to because of miscoordination. And so this brought in kind of multi-agent aspects of how can you have one distant high-level kind of coordinator, but have a team be autonomous as a team. And so that brings in very naturally game theory. The audience of this podcast does controls, does optimization, and the main characteristic there is that we make decisions and we measure the quality of the decisions. But in game theory, the quality of one's decision depends on the decisions of others, depends on the actions of others. And typical examples, they're well-known examples, bring this up in some of my talks. Say in an auction, are you happy with your bid? It depends on the bids of others. In a commuting, if this was very important in Los Angeles, not so much here in Champaign, are you happy with the road that you took to get to work? It depends on the decisions of others, of the roads that they took to work. In society, say back in the pandemic days, should you socialize or not, given having symptoms or not? Well, it depends on whether others are deciding to socialize or not when they have symptoms or not. There's this coupling of decisions. And so it translated very nicely to this multi-agent framework. The bridge that I had actually was looking at manufacturing, where as a manufacturing system becomes complex and that one machine is handing off parts to another machine, which is handing off parts to another machine. Yes, they're all on the same team, But to compute controllers for those kinds of systems is very complicated. So can I view a machine in isolation and view it as a partner, but not the whole system as as one big collection of machines, but view them as individuals, where whether or not to produce something depends on whether or not the other machines are going to take a certain action. So it translated to game theory. And back to luck, I had a postdoc named Gurdal Arslan. He's a professor at University of Hawaii. He was a PhD student of Tamer Bashar here in Illinois. And he had joined my group at UCLA, and he says, what you're describing is called learning in games. And here's a monograph. The name of the monograph was Learning in Games. and it just took off from there. And then from there, I became my research looked into two parts. One is the role of game theory for multi-agent control, but the other was the role of control for game theory, in the traditional game theory sense. And those have been the main two kind of trajectories or paths that I've had in controls and games. And it's been bi-directional.
I'm very excited about this topic in particular because I think it's actually the first time, if I'm not mistaken, that we talk explicitly about game theory. So I feel that we owe the audience a bit of a primer on the subject. I had to study myself. I'm not well versed in game theory. Unfortunately, it's one of my main misgivings, and I'm trying to learn. But of course, there seem to be lots of connections. Mm-hmm. The way I describe it to myself is what happens to optimal control when you're not alone, essentially, in a certain sense. But maybe we can give a bit of an overview, let's say, of what is game theory, what's its historical spine, somehow maybe mentioning von Neumann and Nash, and then 3 ingredients that compose a game. There's a fantastic video lecture series that is online on YouTube that you've given at Högskolan i Halmstad.
Oh, okay.
On game theory that I really recommend it to the audience because at least it helped me trying to understand what this means.
Mm-hmm. So the 3 ingredients is you have a set of decision makers, and these decision makers have choices, and then they have a way that they measure the quality of their choice. But of course, this measurement, the quality of the choice depends on the choice of others. So if we go back to commuting, the decision makers are drivers, their choice is the path, and then their satisfaction with their path, say, is going to be the congestion. Lower congestion is better. It took me less time to go from A to B. But that is a consequence of the choices of others. There is a long-standing connection of game theory with controls, but in the setting of zero-sum games. So in zero-sum games, there is it's an adversarial relationship. And so when we do robust control, say, I want to have good behavior in the presence of all disturbances, or good behavior in the presence of all possible allowable models. And so then it becomes adversarial of the controller versus the environment. But game theory goes beyond the 2-player adversarial situation. It can accommodate multiple players. And so we talked about it for auctions, we talked about it for commuting, but then it becomes relevant for just like resource allocation. If you're going to, one problem that's been investigated a lot in the controls world is, say, robot coverage or sensor coverage. I'm going to send a bunch of sensors out to cover an unknown region. What's the connection from that to a game? Well, a sensor, if it's viewed as an individual, says, should I go to a location? Well, it depends on who else is at that location. And if it's already covered, there's no sense in going there. So my satisfaction with where I should sit depends on where others are sitting. And so you have this coupled interconnection. Now, in the classical game theory world, they talk about solution concepts of saying, if we're modeling, and this is something that's important to distinguish for a controls audience, we're very used to telling others what to do, okay? And that this is how you design a optimal controller, a nonlinear controller, a time-varying LPV controller, whatever. It's not about design yet. It's more about what you think is going to happen, that you have this model of a system where people's decisions depend on the decision of others. How should we model this situation? And the most famous model, but it's not the only one, says that everybody's behavior is optimal with respect to everyone else's. Everyone's choice is optimal with respect to everyone else. So if you and I are engaged, or let's say not just you and I, say an audience is engaged in a game, we're picking left and right for whatever reason. Say, okay, you picked left. This is what everyone else picked. Do you want to change your mind? And if the first person says, no, I'm good. Second person says, no, I'm good. Everybody says, I'm happy with my choice, given the choice of others. Then we're at a Nash equilibrium. And that is a model. It's a model that has its own, it's not without its own criticism. And there's various works over the years in experimental game theory that says, look, here is a situation. It's not a Nash equilibrium. Should this be the model? So there's empirical evidence, challenging Nash equilibrium. There's also analytical evidence, and that you can set up situations where the computation of a Nash equilibrium is intractable. And so you can ask, why should I model people as playing a Nash equilibrium when supercomputers wouldn't be able to compute a Nash equilibrium? And yet it still is relevant. Those two criticisms are not necessarily damning. And there's a line of research that I got very interested in, is asking, and it's the learning in games line. And so in that setting, so let's again appeal to our audience. We've never said the word equilibrium without talking about dynamics first. Okay, you say, here's the dynamics, what's the equilibrium? Now you have Nash equilibrium, but nobody specified the dynamics. And that's the Learning in Games program. And the Learning in Games program is trying to understand, how could it be that interacting agents would ever reach a solution concept such as Nash equilibrium? What is, not necessarily how do they do it, but at least let's start with a plausibility argument of how could simple interactions lead us to something like Nash equilibrium. And that is Learning in Games. It also goes by evolutionary games. And now that we're in the world of dynamical systems, then controls can have a lot to say. And everyone is in feedback with everyone else. Yeah.
First of all, very fascinating. As you say, this is a distinction that took me some time to digest, at least personally, because we're very used to the fact that given a system, I will have maybe one or more equilibria, but there's no distinction in a certain sense, essential distinction between one equilibrium or the other. They are equilibria, they may be stable or unstable, but they're not essentially different notions. While in game theory, as you say, it seems like the focus is more on characterizing how do certain phenomena occur, and maybe how to influence the implementation, I cannot find a better word, of one or the other phenomenon. And something that comes to mind, I'm glad that you mentioned traffic. I was reading some papers the last few days about the difference between, for example, wardrobe equilibria and Nash equilibria when we're thinking about routing in a traffic network, for example, and where the system operator could tell everyone the direction to take and is effectively minimizing congestion for all. But when the players are selfish agents with their own objective, then the equilibrium that tends to emerge is a different one. And it's not necessarily the optimal for all, but it's the optimal for each individual, as you say. And so there's a bunch of papers that we can mention here. I think one that seems to have started it all is dynamic fictitious play, dynamic gradient play, and distributed convergence to Nash equilibria, if I'm not mistaken. There's a couple before that seem to be related. But I feel that this is really the one that really sucked you in.
Okay, so as I mentioned, there's kind of two arcs. One is using game theory to design multi-agent systems. And then the other is what dynamics and control can say about the learning in games question, which is trying to address how could certain solution concepts emerge. So here we have to kind of set up some context. A paper came out by researchers Hart and Mascalel that gave a particular game and say, here's a setting, and no, it has a Nash equilibrium, it has a unique equilibrium, but there is no reasonable learning rule or dynamics that would lead to this equilibrium. So what's the definition of reasonable there? The terminology is unfortunate, but it was called uncoupled. So uncoupled meant that I can react to what you do, but I can't react to why you do it. Okay, so let me give a traffic example. Suppose now I'm minimizing congestion. I don't like being on the road. So if you're on the road, I'm going to try to avoid busy roads because that's my intent. Now, maybe you like being on the road. Okay, you like your car. You want to swing by a particular restaurant. You want to be late to a meeting so you don't have to attend it and you can just blame the traffic. Okay, you have your own intent. I can react to your presence on the road, but I can't react to why you're on the road. And that's what would be called uncoupled learning, a learning rule where we can react to what others do, but not why they do it. And they showed for this particular game, it's called the anti-coordination game. Just use that label. They showed in the anti-coordination game, no uncoupled dynamics, no reasonable dynamics will ever find the Nash equilibrium. And it was kind of one game that is very, would make then the emergence of Nash equilibrium kind of very, not unlikely, impossible. But it turns out that it was not uncoupledness that was the barrier there. And that's what that paper, Dynamic Fictitious Play, establishes. So let me make an analogy to control systems. You have a plant with an output. It might be stabilizable with static output feedback, or it might not be. Suppose I need dynamic output feedback. I wouldn't call that plant not stabilizable. It's just I need dynamic feedback. Mm-hmm. The same thing. If you allow me to use memory, I can still be uncoupled, but find the Nash equilibrium. And so I'm not getting more information. I'm being more sophisticated in how I use the information that I have. So for example, just reacting to a trend. And, in the saying in the stock market of the trend is your friend. And so instead of reacting to what things are right now, let me react to where they're heading. Okay. And if I react to my kind of anticipation of where things are going, then you can get convergence to Nash equilibrium with uncoupled learning. And not just for the anti-coordination game, that was 20 years ago. Now let's fast forward 20 years later to the PhD thesis of Sarah Tunsi, who defended earlier this year. Mm-hmm. Actually, it's generic that for any Nash equilibrium, there is an uncoupled learning rule that can find it. I don't know necessarily what that learning rule is, but uncoupledness is not the problem. And so there are other implications of that work. But it kind of, if you want, rescued Nash equilibrium in the sense that, yes, uncoupledness is not a problem. Now, there may be other problems, but uncoupledness is not one of them. So that was that work. That was a joint paper with Gurdal Arslan. And then it kind of simmered for a while until we kind of figured out the general story of that discussion. So we showed that for any Nash equilibrium, there are uncoupled learning rules that can find it. But we also show that it's not a universal structure. For any learning rule, there's a game out there for which that learning rule doesn't work. And so let me say it again. For every game, there's a learning rule that works. For every learning rule, there's a game for which it doesn't work. What I really like about this is, well, first of all, I have a very simple way to remember this result. I'm quoting a TV show from 1970, and it was that there ain't a horse that can't be rode, but there ain't a man that can't be throwed. Okay, and that for every horse there's a rider, but for every rider there's a horse, and then that kind of neither one is universal. Okay, but one of the things that I really like about that set of results is that it showed kind of the versatility of controls ideas in a setting where it was probably unanticipated where they would be used. The results that we used in, for example, was in the 70s, there was a lot of work on so-called decentralized control, which became popular with distributed control. But in decentralized control, we just asked, is it possible to stabilize a system with a diagonal controller? Mm-hmm. The motivation was large-scale systems that are not allowed to, where the controllers are all local and they're not allowed to talk to each other. That was the motivation. That was the key to answering this question. Diagonal controllers is like uncoupled learning. Mm-hmm. I'm not allowed to react to your signals. I can react to what you do, but not why you do it. And so this connection allowed us to use control techniques from the 70s that were designed for very different reasons to this setting of learning in games. There's another result related to controls for learning in games, and that is that although some equilibria are always learnable, some of them should not be learned. In that the learning rule that works is inherently irrational. I can say what irrational means, but it's a learning rule that just doesn't make sense. It's uncoupled, but it doesn't make sense. And the results that we use there, again, came from the 70s with people asked the question, when can I stabilize a system with a stable controller? It was called strong stabilization. We showed that those results apply to learning in games as well. So you have things like decentralized stabilization, strong stabilization, simultaneous stabilization. These are all questions that came in controls under very different motivations in the 70s and 80s. And then turns out that they are very relevant for the learning in games to answer questions, learning in games, what is achievable, what isn't achievable. And I'm very excited that these kind of things can come back in ways that were not anticipated. And no offense, it's also kind of fun to use techniques that no one under 40 remembers.
So indeed, I have a bunch of comments actually with regards to what you just mentioned. So first of all, it seemed like, the result of the paper we just mentioned, and also many ensuing papers and results, could be actually fleshed out only by a person who is well-versed in quote-unquote old-school control. I would argue that in particular in dynamic fictitious play, dynamic gradient play, and distributed convergence to Nash equilibria, you were essentially highlighting the relevance of anticipatory derivative type of actions, let's say. Mm-hmm. So the first thought that I had was, well, this is like adding a D to a PI mm-hmm. controller.
That's it. Mm-hmm.
But for someone who knows controls, it's illuminating in a certain sense, or it's very exciting that you can say something so new in a different domain, I guess.
Mm-hmm. There it's also double-edged. So let me mention there are other communities that explored similar ideas, like in optimization. There's, say we're familiar with gradient descent, but there are some optimization techniques that use the history of the gradient. And so a heavy ball, accelerated, or optimistic gradient. It turns out that optimistic gradient descent is exactly proportional derivative gradient descent. The double-edged part, and this is actually now opening the door to some jiu-jitsu analogies. The double-edged part is that, you describe it and says, oh, what you're doing is proportional derivative. So for one community, that's very natural and perhaps obvious. For another community, and this was feedback that I got, is like, why would anyone do this? That's so bizarre. And so which is it? Is it, it depends on who you're talking to, that it's natural or unnatural to introduce that. It looks very concocted to one community, whereas for another community, it goes from bizarre and concocted to natural and obvious. And so the connection to jiu-jitsu is just being comfortable with discomfort. Mm-hmm. Is that when you kind of go to another community, they call it your comfort zone for a reason. Mm-hmm. And when you're out of your comfort zone, you're uncomfortable. And it can be uncomfortable trying to kind of relay a message where folks don't quite know how to receive it. There was kind of similar resistance, if you will, although this is evolving, to ideas of passivity.
Which I'm very excited to talk about, actually. Very, very, very excited to talk about.
Yeah, which were, again, ready to be imported into that world of learning in games. So, but this is all like controls for learning in games. Mm-hmm. It's not so much about game theory for multi-agent controls. That's a different arc. As
a matter of fact, I can take this tangent or many other tangents. I'm quite mm-hmm. excited, as I mentioned, about the application of dissipativity ideas in the context of games. It looks very natural to me, and in reading also about your journey, somehow I had the question, why would this not happen before, in a certain sense? But I'm not as versed in game theory as I should be, so then maybe you can actually elaborate on what was your trajectory after these first few papers, like in early 2000s onwards?
Mm-hmm. So there was a researcher, Bill Sanholm in Wisconsin, who's since passed away. He wrote pretty much as now a gold standard in monograph on population games and evolutionary games. And so it's be well worth tracking that down. And so he had a paper with Joseph Hofbauer and Sanholm, where it was called stable games, which is a weird terminology because a game is a static entity. Why would you call it stable or not? So let me give that paper a different title. Instead of calling it stable games, let's call it games for which there are many learning rules that are stable. Okay, that would be the long, clumsy title of the paper. Here's a class of games, and all of these learning rules happen to converge to Nash equilibrium for this class of games. So this class of games must have something special. And then what we were able to realize, and this was a paper with PhD student Michael J. Fox, that actually it wasn't the games that are special. All of the learning rules had something in common, and it was a passivity condition. And it turns out that those games were just the complement of passive learning rules. So passive learning rules has been hidden. All of these learning rules happen to be passive. And this was just the complement of passive learning rules, where these so-called stable games, which are now called contractive games, which is connected to contraction theory, which is connected to monotone operators and variation inequalities. You find it's bound to happen. You just find these connections once things become more apparent. So it turns out that passivity was lurking in all of these learning rules since forever. And what got us also excited about this is that, as you know, passivity doesn't really care what's the dimension of the system. So this was a way, going back to the work of dynamic fictitious play, how can we talk about learning without specifying the dimension while allowing higher order auxiliary states, whether it's derivatives or other integrators or you name it? Let's just look at inputs and outputs, and that way we don't care about the dimensionality that's underneath. And so that was the motivation, kind of twofold. It wasn't so much to bring passivity, but just how do we talk about learning in games without restricting ourselves to the dimensions of the learning rules. And it was a natural pairing, and now there's been a lot of work pursuing that. There's a very nice paper in Control Systems magazine by Lacra Pavel that gives an overview of passivity and dissipativity and captures a lot of the recent results. And there's a handful of names. I won't risk listing them. I'll just mention that paper since it's a survey article and a survey tutorial.
I definitely wanted to mention at least Lacra Pavel being active in this domain. I'm also glad that it was one of the papers. It wasn't an easy decision on my end to decide which papers should I actually look at in preparation of this episode, because there's so many. Many are actually giving, at least in my very humble opinion, surprising results. So the one that we just spoke about is Population Games, Stable Games, and Passivity with Michael Fox, presented in 2012 in Hawaii at the CDC, our main conference. And as you say, here you show that stable games are anti-passive systems, essentially, if I can phrase it in the language of dissipativity, as we're speaking. With Michael Fox, you go on and characterize also other types of games. And in parallel, I can see you working also with a number of other talented students, one of which is Jason Marden, also together with Gurdal Aslan initially, and then on your own, you talk about cooperative control and potential games. Then also, as you mentioned, evolutionary games with other people, Shinyu Park, Nuno Martins, but also weekly cyclic games. How should I and also a potential reader orient themselves in this landscape of, it looks like there's a zoo of games for each of which we can say we can use tools from controls. How does one go about understanding game theory from our perspective as control theorists?
So you mean you called it a zoo? I illustrate it like this huge matrix in my talks.
Okay.
And so you can think of the rows of the matrix. I show this slide exactly. The rows of the matrix are types of or properties that games may have: zero sum, potential, weekly, acyclic, two-player, various characteristics. And then the columns of this huge matrix are different types of learning rules. Okay. And then the elements of this matrix are what happens. So when I take this type of game and that type of learning rule, this is what's going to happen. Or this is what's guaranteed not to happen.
Mm-hmm.
For example, if it's the anti-coordination game with a certain types of uncoupled learning, you will not see a Nash equilibrium. If it's a zero-sum game with something called replicator dynamics, you will see chaotic behavior. So the landscape does look like that giant matrix. And in my talks, I have something that I call a meta theorem, which looks a lot like the party game of Mad Libs, of just give me a game, give me a learning rule, and then I create a sentence with this game and this learning rule. For this type of game, under that type of learning rule, this is what's going to happen or not happen. Now, you point out that, yeah, it's just there's a lot of different special cases. But let me come to something that's a bit more important than that. And it took me a while to appreciate this as well, is understanding why this community is asking the questions that it does. And we have to really appreciate what's behind the question being asked. So let's look at this idea of uncoupled learning. They showed that if I don't know the intent of other actors, there's certain things that can't happen. Fine. But if these are programmable devices, if they're robots going out and exploring a field, well, I'll just tell you my intent. Why do I have to keep that a secret from you? So if we're doing cooperative control, game theory is a lens, but it kind of also brings in certain constraints that are unnecessary. And that at the end of the day, it's about distributed computation and not so much about the game theory. And yes, one can use game theory for coordinated or multi-agent systems, but the whys, why am I doing it this way? Or why am I imposing this constraint is different from the why am I imposing this constraint when it's the traditional game theory setting. So let's stick with uncoupled. I'm not going to tell you my intent because I'm a human and you're a human, and I'm just not going to tell you my intent. It's a good model. How about for programmable robots, mobile robots? Maybe there's energy considerations. It takes, I want to save battery. Maybe there's stealth considerations. I don't want to be discovered. Maybe it's unreliable communication channels. That is the why that leads to the same, okay, we're not going to talk to each other, do a certain secret message passing. And so to help in navigating the landscape, it helps to come from a specific question in mind. Am I designing programmable devices, or am I modeling human decision-making? Now, what's very interesting is that these two worlds have come into collision now in the modern area of multi-agent or agentic AI, and that they're kind of, you have programmable devices that are adaptive, interacting with adaptive human decision makers. And that's leading to all kinds of kind of surprising outcomes. And yeah, that's something we could talk about as well. But I think to help navigate is, why am I asking this question? And that will more naturally lead you into the kind of the setting that will be fruitful.
So you serving me many assists. This is gonna be a long episode. Whether it's good or bad, we'll leave it to the audience, but I'm having too much fun. So, okay, first of all, this perspective of framing cooperative control problems, I would like to give the spotlight to at least one of the papers that I've seen really framing cooperative control problems as learning problems in games, is this paper titled Cooperative Control and Potential Games with Jason Marsden and Gurdal Aslan. Also, there's a very nice review called Game Theory and Control on the annual reviews of controlled robotics and autonomous system, also with Jason Marsden. Found it particularly useful for me, at least as a newbie in this field, to understand what we're talking about. And also, okay, I'll let you choose what to continue on. I have 2 or 3 comments that I'd like you to spend a few words on. Okay. So the first one is related to this matrix that you mentioned before, that we're populating with different rules, and we're trying to understand what sort of phenomena, where are we?
And games, yes.
Yeah. So the first question is, where are we at actually trying to flesh out this full matrix? The second is, I've seen from your trajectory that I guess at some point here, we're moving from LA to Georgia Tech, and then at some point even to KAUST in Saudi Arabia, that I'm very curious about, like why and how did that happen? But in particular, in that period, you also work on applications of these methods, for example, in self-assembly or, as you say, programmable machines, which I find particularly fascinating subjects. For a control theorist, it's impossible not to be fascinated. And third, I'm very curious, as you say, to hear your perspective about this multi-agent world where game theory does not care whether on the other side there's a person or there's an algorithm or an institution. It doesn't matter. So how, in a certain sense, my question is, how do we defend themselves from the dangers, in a certain sense, of AI gone wild?
So actually your first question and the third question, I think are merged. Like, where are we in the matrix and this multi-agent world? And so we have, say, using game theory or whatever method you want to do to design cooperative control systems where the control system is a team rather than an individual decision maker. And then there's also in that matrix the understanding how classical concepts in game theory, such as Nash equilibrium or other solution concepts, can emerge through dynamics. All right. That's been the traditional, historical rather, kind of motivation behind that matrix. But now I think the motivation has changed, and I think this will breathe new life, going back into that what we said of third-party impact on research cycles. And I think the new question is not so much how can we justify things like Nash equilibrium, but rather how can we understand multi-agent adaptive systems in a way to save ourselves from ourselves. So this is, for me, my doomsday scenario. It's not Skynet and self-awareness, but it's rather adaptive systems that are being increasingly endowed with kind of consequential decisions that are being deployed in the presence of other adaptive systems that other people designed, that other agencies designed, and being deployed in the presence of humans who are also adaptive. And we don't know what the edge cases are because it's adaptive. The edge cases are to be determined. And so just understanding what is going to happen, and are there guardrails? Do there even exist guardrails that we can put on all of this, everyone's adaptive systems? So here's a couple of examples. One, there are news reports on, say, drivers in rideshare exploiting surge pricing. So surge pricing is when there's a shortage of drivers. It's an adaptive algorithm. So there's a shortage of drivers, we're going to raise the price. So the drivers go turn off their availability, artificially create a shortage, and now turn on their availability with the surge price trigger. So here you have colluding. So you have adaptive drivers taking advantage of an algorithm. Mm-hmm. There was a research paper a couple of years ago. It was a simulation study that had pricing algorithms learned to collude to artificially raise prices. Say, if I sell on Monday and you sell on Tuesday, we can make more profit, both of us, okay? So they're colluding. What's interesting about the second type of collusion is there may not have been any explicit agreement, but rather they just figured this out. And I think this is a very interesting research question of just what constitutes collusion. We didn't set aside in a dark meeting room and say, let's do it this way. We just stumbled on this behavior that happens to be better for the both of us. Is that collusion or not? So, and there are people investigating what is collusion and what is algorithmic collusion. There is a talk by Vincent Conitzer that brought up an example from Amazon a decade ago of a book that was offered for sale, like a garage sale book that was offered for sale for $20 million. And what happened is you had two agentic pricing algorithms. One would undercut the price of the other would overshoot the price of the other. But the ratios were such that the offer price, if you wanted it new, it was $20 million. If you wanted it used, it was $40. Okay, so, but this was an example of an edge case that was unanticipated because you had two different people programmed to different adaptive pricing algorithms. But if you look more recently, and it's easy to find headlines of AI agent does this, AI agent lies about company policy, AI agent wipes clean the data records. These adaptive systems in the presence of other adaptive systems can literally be chaos. Mm-hmm. And so I think the matrix now is not about how do we understand game theory or how do we design cooperative control systems where we're the ones who are programming all of the robots. but rather what happens in a world where everything's agentic and everything is adaptive and everything has significant authority, and what are the guardrails, or do even guardrails exist? So I think it's breathing new life into this set of questions. And I'm biased, but I also think that systems and controls is ideally positioned, because we are in the world of feedback, is ideally positioned to try to address these sorts of questions. Because like I said, feedback control is our domain.
I take this as you say, as a double-edged sword. This seems to be one of the leitmotifs of today's chat. So on the one hand, it's good news for researchers because there's a lot to understand, really try to come up with measures of containment in a certain sense of what can go wrong. But at the same time, I feel that this also brings some awareness about the fact that those catastrophic events can and probably will happen. And we know it already in a certain sense, because we are closing the loop with so many players that can make decisions in the world, thanks to access to the internet, for example, and God knows what are the outcomes, I guess.
So you mentioned the move to KAUST. And so KAUST is King Abdullah University of Science and Technology. And so at that point in my career, I'd been a professor for about 25 years. And so some backstory there, KAUST was a new research university on the Red Sea with students from all over the world, faculty from all over the world, staff from all over the world. It was a research university, as you can imagine, abundant resources. It was a startup university. It was only 5 years old at the time that I joined. And I have a personal story of having Middle East connections, being of Egyptian heritage and wanting to see a success in the region. But most of the professors did not have Middle East connections. Everyone brought their own story about why they're there. And for me, it was about, I was at Georgia Tech at the time. I'd been a professor for 25 years. And I said, what is the next 5 years going to look like? They're going to look a lot like the previous 5 years of a few more papers, a few more projects. And yeah, that's fine. But here's a chance to do something that's very different, to be part of an experiment where one might have an impact, even after leaving. And my standard joke about this transition is, so at Georgia Tech, I was in a department with over 100 faculty. That was the ECE department. And I would say that the only thing stopping them from replacing me is noticing that I left. Okay, it's just it's a big place. Okay, whereas at KAUST, an individual can have an impact. And so a part of the appeal was just having a different challenge of what can I do that may have impacted institution even beyond my presence there. And then another part of it was, as I mentioned, there were abundant resources. Really, we were not writing proposals. There's a lot of parallels to the ETH model, actually, and the EPFL model of every professor gets some baseline funds. So also as a new university, it's not going to be the same as, say, Georgia Tech students. But if I wanted Georgia Tech students, I would have stayed at Georgia Tech. So I put a lot more of my energy into mentorship, and as a result, had a connection to my group that I never had before. Because I'm not writing proposals. I'm not worried about getting a student who can support a project. The goal was the development of the student through the research. And people do talk about research universities. My personal view is universities are only about education, and research is a vehicle for that education. But we're not research labs. That is consequential. It's an indirect outcome. But we're not research labs. We're only educational institutions. And even postdoc is about continuing education. So I put a lot more energy into mentorship, and I think it was a very rewarding time there. Now, I did mention abundant resources. So all of these ideas of cooperative control, we can try them. We developed a robotics lab. It had a motion capture. We can try them indoors. Pretty much with resources, we had a full-time lab engineer in Quat Teleganov. He's now with Amazon Robotics. I was very lucky with two of my first PhD students to be the architects of that lab, Mohammed Abdulkader, Mohammed Shakura. I would just come in with a white glove and check if there's any dust on the shelves, but they really put the whole thing together. If you had an idea in the morning, you could test it in the lab in the afternoon. It was really well functioning. And also with Saudi Arabia, you get 362 days of sunshine. Okay. So you can try it outdoors And we were on an isolated compound, so we really weren't encumbered by restrictions of when to fly and where to fly. And so we could try some ideas right away. And so that was a great experience. And to move more towards kind of implementation of some of the algorithms, truly testing them, and also more towards mechatronic design. I had, I can say on my CV that I have 17 patents. I would rather say that my name is on 17 patents because I was really a ride-along for those. And in particular, one by Father Latif. He was a PhD student and he's working for Aramco, who designed a drone system to land on a pipe, release a crawler, do ultrasound testing on the pipe, go back into the drone and fly away. And that now has been kind of handed over to a commercial production and resulted in lots and lots of patents as well. And so it's a different type of contribution. There was a very different experience. I got what I was looking for. The nature of being in the Gulf is that, it's always temporary. And so I got to spend a good 6.5 years there. But it was a wonderful experience. And what's lasting, though, as I mentioned, is the connection to the group that I had at the time. And some of them came to Illinois with me as well. But the connection to the group, it was never before, and I don't see that happening again.
Fantastic. KAUST is also located an hour north of Jeddah, right?
That's right. Perfect. Yeah. So we would see people travel to see sunset over the ocean. And my office had the sun setting over the Red Sea to the point that I would close the blinds because I don't want to deal with the glare. Okay, this is a lifetime view, and I was shutting the blinds because it had a glare on my laptop.
You had to focus as well.
Yeah.
Yeah, indeed. I'm glad that you brought up many other elements we didn't touch on yet. First of all, I could see in your CV, let's say, a surge of patents sort of out of nowhere. And then like from 0 to 17 in the range of like 5 years or so. And also your focus, which I appreciated a lot actually, on applications now of these ideas in cooperative control and multi-agent control to lots of very funky in a good way, applications like self-assembly. I've seen these videos of squares bouncing onto another and assembling into a shape that you programmed. Similarly, swarms of robots. I've seen that you're still active in a sense on those themes. Like I've seen a survey coming out recently.
An aerial robotics challenge, is that one?
Yeah, exactly.
Yeah, I know. But now I'm back in the U.S. model, and so it's I'm not going to have those resources or weather to do things. But yeah, it remains of interest. I'll probably be moving more towards the human-algorithmic interaction aspect that we chatted about. Yeah.
Maybe, we could take this as a soft transition towards the end of the episode, indeed. Okay, I could mention many publications, and I've seen you also speak publicly about the interplay, as we mentioned, not only of AI and multi-agent systems, but also the role of control in optimization. I've seen a few papers of yours also taking a controlled perspective on, for example, a very cool one on optimization and, the relationship between constrained optimization and feedback linearization. Very, very cool paper. I didn't make that connection, seeing that you could see exactly, sequential quadratic programming, or also known as SQP, as essentially a version of discretized feedback linearized control system. Fantastic idea. Of course, there's many active players in the domain of connecting controls and optimization. I could name many names, but I think, again, it's inelegant. So I'll leave it to the audience. I'm curious about where you're going and what are your foci of interest today?
I think mostly going in this direction of everyone's adaptive, agentic AI, where some of that AI is natural intelligence of humans, trying to understand what will be the outcome of a system of many adaptive components where you don't have a single programmer. It's complicated enough when you had a single programmer, but now you don't have a single programmer. And some of these are humans, and what will be the implications, whether it's algorithm-human interaction or robot-human interaction, where the difference there is their physical consequences and not just algorithmic consequences. I see this as my main interest going forward. I am a department head, and that comes with its own kind of obligations, let's say. So it will be kind of tempered here to those other duties as well.
And quick question, and then maybe we can transition, as I mentioned, towards the end. But do you see a role of social sciences coming into the picture, given that now we're taking into account the fact that humans are in the loop? And so there's all sorts of questions intermingling, let's say, with this idea. I'm thinking of, for example, fairness in designing certain systems, but also, I don't know, behaviors that it's basically impossible to model with mathematical models, but we can only probably, I don't know, use behavioral economics or other tools to quantify, in a sense, behavior. What's your take on that?
So you're seeing these connections being made more and more explicit of social sciences, economics. I mean, game theory has, of course, a very historical, traditional connection to economics. But as you mentioned, behavioral economics, if we're going to be kind of putting in models of how algorithms interact with humans, we need better models of what humans will do. And adaptation and learning is part of that. And this is also kind of being widely recognized in the controls community, as we mentioned, through the cyber-physical human systems. There are a few institutes that are dedicated to this. One that's kind of close to mind is IDSS, that was kind of launched as an inaugural director by Munzer Dali of the Institute for Data Systems and Society, where you have all of these folks under one roof, kind of sharing both models and techniques and motivating problems for collaboration. But if we want to make something effective, yes, for interacting with humans, sure, I can, in a naive way, say a human decision maker is going to be another PID controller. But if I want to do anything kind of more sophisticated, it has to be through collaborations and through data. And here I'll mention something about the path of least dislike. When we're making decisions, we make career decisions, lifetime decisions, based on what we thought was cool when we're 13. Okay, and it's the reality. Okay, and there were some kind of I didn't go into social sciences, and part of that was a naive dismissal of, well, what is it really about? You can't do repeatable, controlled experiments. And so none of it is very grounded. And that led me away from that. Now I find the same characteristics as what makes it appealing, is that you cannot do repeatable, controlled experiments. You can't just model someone as Newton's law. And that's actually what makes it all the more exciting to me. And so, I've kind of come fully around on that. But it will require, if we want to do anything that's not kind of shallow or naive, and is to collaborating with folks who do this and have put a lot more attention, towards human decision making to design human systems. A nice example would be like the problem of platooning that people have investigated in controls. It's easier to design platooning if they're all autonomous trucks. But you make one of those drivers a human driver, and suddenly it's very different. It's a very different challenge. And the fact that, as I said, you cannot do repeatable, controlled experiments. You cannot model a human as F equals MA. It makes it interesting. I'll draw here another analogy. So it turns out my son, had an amateur career as an MMA fighter. So just the apple falls far from the tree. So what I found really curious about, so he had 3 cage fights, he won them all, he didn't deliver damage, he didn't take any damage. After beating each other's brains out, they hug, okay? Because they understand the intent of the engagement. So when you ask a car to go 60 miles an hour, or when you knock on a table and it resonates, or it doesn't ask you, why are you doing this? It's not asking what's your intent on taking this action. But in dealing with humans, a big part of it is the intent. And so when we're dealing with, for example, human-algorithm interaction, we already question the intent of algorithms. When you get a product recommendation online shopping, is this really what I'm looking for, or are they trying to push a product on me? So we've already kind of questioned the intent of algorithms. Algorithms are now questioning our intent. This idea of jailbreaking like chatbots. when we ask it a question, it wonders, why are we asking this question? And are we up to no good in asking the question that we're asking? So this is really a new element. And again, to try to address these things in a serious way will require bringing in all sorts of tools from all directions.
Indeed. I generally agree, let's say, with this vision. I was also curious, I mean, now it seems to be a good time to bring back now the tangent that I didn't take before about jiu-jitsu. So how, maybe it's a good time now to respond, how is jiu-jitsu related, since you mentioned MMA, how is jiu-jitsu related to controls and your path?
So there's two kind of sayings. So first of all, the literal meaning of jiu-jitsu, as far as I'm aware, is like the gentle art. Okay. And one of the connections is just being comfortable with discomfort. And this is something that every PhD student learns the hard way, if not any other way, through their experience. And this is something, again, back to saying what our parents say. The first conversation my advisor had with me is similar to the first conversation I have with incoming PhD students. It's like, why are you doing this? Because and if you're asking a cost-benefit analysis, don't do this. You're going to be on a path where you're going to be stuck. You're going to be stuck for several months. And your friends, they're going to be moving on with their lives and getting jobs, careers, families. You will be questioning your decisions, your life choices, and being stuck. And so, but as an outcome, and this is again referring to Mike Athans, he felt that the PhD was about going through this cycle of being stuck and not knowing what to do, and then emerging from that. He said, that is the PhD. And along the way, you're going to become an expert in something, you're going to write some papers, but that's not what the PhD is. The PhD is going through that cycle and being comfortable with your discomfort. And so now when you go to start a new job or start a family or many others, it's you're uncomfortable, but you know that you just breathe and wait for the right time that you can kind of figure your way, work your way out. And now this happens in an academic career. We get rejections on papers, we get rejections on proposals. Sometimes your class is going sideways, you're not really having the connection to the students that you want. If you enter a new community, as we said, we face lots of uncomfortable situations over the course of a career. And it's just being comfortable with discomfort is one. And then the other connection, at my previous school, they used to give the advice of, their characterization of jiu-jitsu was don't get tired. It's all about not getting tired. If you're in a conflict, you're expending energy, but you want to expend energy wisely and let the other person get tired. So I think there are different kind of strategies one can take to not get tired, but there's some things that we find ourselves doing that are just not effective. They're not effective in timing or leverage. What would be the analogies? Not making certain simplifying assumptions. Okay, I want it to be this. You're going to get tired. Make the simplify until you get to the essence. That's one thing. Another thing would be, like a strategy, is to work on projects that are qualitatively different. What do I mean by that? There's some things that are going to have a longer time scale with very uncertain likelihood of success. And there's some things that have more immediate gratification. Personally, even if I'm working in theory, I like to build a simulation of the theorem that I'm trying to derive. And that has immediate gratification. And at least one doesn't get in a rut of this long-term pursuit of something that may or may not pay off, that I'm able to change tracks in my mind and refresh my mind when I go back to the other track. And, there are a few other things that we do that are just not efficient or questionable decisions, making decisions for the wrong reasons, working on trendy topics, I think, is one. Trying to beat a deadline when there's always another deadline, around the corner. Why don't we just
I can relate to that.
Take the time to do it a different way. And also forgetting about and this goes back to my KAUST experience, forgetting about the personal element. The personal element is very refreshing. And part of being an academician is a lot of what we do is what you and I are doing right now. We're just talking, and both of us are at work. Okay,
in principle,
and
yes.
Yes. So enjoying the personal aspect is refreshing as well. So these two parts of being comfortable with discomfort and not getting tired, we're in it for the long run, and how to kind of conduct ourselves accordingly. Now, mistakes happen. I've made my mistakes in the academic world. I've made my mistakes in the jiu-jitsu world. We called it the gentle art. I've been choked unconscious.
Oh my. Oh my.
And I've choked others unconscious. And in both cases, it was a mistake. One of them was my son, so I don't feel that guilty about that one. At least I did it when I could. Yeah. And so, this is advice. I don't want to be hypocritical in saying this is how I conduct myself. It's a lifelong journey of applying one's own advice to yourself along the way.
Yeah, indirectly, you replied to anticipated also the question on advice on future students and the connection to jiu-jitsu. And if I can summarize it, is somehow it feels like a tool to be present, just like a PhD is in many ways, as you say. So the journey is about realizing that you are part of the journey. You're going up and down, and the world is not going to end. You're going to come out of it. I hope this is also I hope that many will listen to this episode, because I think it brings a very positive message. The PhD blues are real, but at the same time, it's also true that you come out stronger. And jiu-jitsu, like a PhD itself, can be means to a realization in a certain sense, as you say. And I have one last question, because I heard you have hot takes about the use of ChatGPT in education. I'm wondering, what are your takes on that?
Yeah. So I think we're at a position where we need to kind of reassess what we teach and how we teach it. And here I like to use the phrase back to the future on what I think is a reasonable trajectory going forward. So let me preface this with a story. So as I mentioned, both of my parents were professors. Actually, they were math professors. And my dad, he saw that I was getting a little too arrogant in acing all of my ODE exams. But if you remember, the ODE differential equations class we took was the pattern matching. Like, here's a differential equation. What's the solution? What's the solution? What's the solution? So he brought out this thin book called Introduction to Ordinary Differential Equations. He says, you can't solve one problem in this book. Okay. And it wasn't about constructing a solution, but it was about manipulating ideas. And I remember this very clearly. And let's say he challenged me to 3 questions. The first question I couldn't do. The second question I couldn't do. The third question, and this ended up like a template for my research, I realized that if I took the first 2 questions axiomatically, I could solve the third one. Okay, I could just, and he never noticed that before, so we called it a tie. But my point is that you can take a whole class in differential equations without solving a differential equation, but rather you're understanding the differential equations. You're focusing on the intuition and the insight, but not the construction. Mm-hmm. And so I think that maybe this is where we're going to go with education in general, but let's stick to controls education, that we can focus on the insight of control systems, and things like robustness is not going away. Things like trade-offs of performance and robustness is not going away. Things like some systems are harder to control than others is not going away. Mm-hmm. And focus on that kind of insight. But when we want to construct or design a controller, then we throw it to the CPUs and the GPUs and let it do that. Mm-hmm. And so this is what I mean of back to the future. We might be doing education back to like 50s style, where we didn't have computation and just focused on pencil and paper and insight, and then let the construction, we know what we're looking for when we throw it to, the big machines to do the actual construction of solutions or construction of controllers. I don't know if that will be the outcome. And maybe I'm just grasping for anything to keep us relevant, but I see that as a path going forward, not just for controls, but I think for a lot of engineering education, of using the computation as a partner and focusing back on the intuition.
I think it's a very positive prospect in a sense, compared to the other prospect of, letting our brain rot, as they say, and just throw everything to ChatGPT, and because we don't use it, our brain will be gone. I think actually the idea of focusing on insight is much more positive in many ways.
If you allow me one more thing, there's a game theory researcher, Ariel Rubinstein, who makes the following comment about games. He says, we use the word model because it sounds scientific, but actually what we're talking about is fables. and so if you hear the story of the tortoise and the hare, the response is not, that's not realistic. Who is the timekeeper? Okay, the response, you don't say that this is not a realistic model, but you say that there's a story that parallels life and it has a lesson, and the lesson is relevant in life. And I think that would be like with controls. If we're going to teach linear systems, why teach linear systems? I don't need to have a course in linear systems theory to design controllers, but there are lessons that it's more about the abstraction now of linear systems, and that there are life stories within the world of linear systems that are still relevant. And so I just don't accept blindly what's being given to me by the computational devices. I think we're going to move towards fables and morals.
It's really the Swiss knife that you mentioned before. Endow students and future generations with a Swiss knife of lessons that they will carry throughout life. And I resonate with what you say. I think another complement will be the fundamentals, as you mean. Well, I think this actually brings us to the end of the episode, Jeff. It's been a roller coaster as much as I expected, and also a wonderful roller coaster. I enjoyed so much learning about your research and everything that you produced in this academic world. Thank you so much for accepting the invitation and joining us.
Thank you for the invitation, and thank you for all of the preparation that you do in this episode and every episode that I've listened to. And then I know other guests have commented on this, but it's genuine. This was a very fast 2.5 hours for me. So thank you.
Same for me.
Thank you so much.
Thank you. Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.